This is Free Range Digital Design Foundation Modeling Chapter 15, Lecture Number 2, and we kind of gave the foundation of modular design in the previous lecture. But what we're going to want to do in this lecture is do a couple example problems, but first we'll go a quick review of the design process in general. Modular design approach, once again, you're going to develop your own style with this. Since this is the first thing we're doing here, here's like a set of rules. You need to read and understand the problem, always the first step, and from reading and understanding it, you should be able to generate a top-level black box diagram showing the inputs and outputs of the circuit. Not necessarily what's inside the box, but how the outside world sees that box. Next, what you want to do is look at your problem description and decide what lower level modules you're going to use in your circuit. After you decide all that, you're going to need to connect those modules both to each other and to the inputs and outputs of the circuit. And by all means, if you design your own module, you have to provide a model for that or a description for that somewhere. We try to use only standard modules in our designs. Once you've completed the design, the next step is take a few steps back and look at it, make sure everything's labeled correctly. Particularly, make sure that the whole diagram itself, top-level black box diagram, has an appropriate label. Lots of modules in your diagram, make sure they're all connected properly, and particularly make sure all inputs are connected to something. It's not so much important with the outputs, but make sure the inputs are connected to something. Make sure all the signals have appropriate labels. It doesn't have to be every signal in your diagram, but it should be the important ones. Make sure all your bundles are marked with the bus bar indicator, and make sure they have a width of some number like that. Make sure all your lower level modules have names. They should be self-commenting names, and make sure you've provided a model for all non-standard modules. The first circuit here is what we're going to do is design a circuit that changes the sign of an 8-bit signed binary number in radix complement format. Changing the sign simply means taking a 2's complement of it. So when we took the 2's complement of a number as humans, we started on the right side, looked for the first one, we kept it, and then we toggled all the other bits as we worked right to left. Now that's for humans. What we want is to use the hardware approach, and 2's comp of A equals A bar plus 1. So you complement all the bits, which is what this term does, and then you add 1. That's what we're going to use in hardware. For realizing that, this is what we're going to use in hardware to do a 2's complement. What do we need? What kind of interior modules are we going to need for this? So let's take this step by step. This is going to be the top level module. I'm just going to call it circuit here, and I'll say in, and they're both 8 bits, and there's my step 1. So this completely describes the interface to this module, which means how the outside world sees this module. So next we want to take an inventory of the interior modules that we're going to need here. So we're going to be implementing this equation. So I'm looking at that. I see a plus there, and I'm going to have to do some addition, and I have one circuit that does addition for me, which is a ripple carry adder. I am going to go ahead and plop that down. I think I'll go ahead and mark this. The idea here, there's actually can do this problem a couple different ways. I am going to do both ways on this one. So what's going to happen in this thing is I'm going to need to complement A, which means it's an 8-bit signal, so I'm going to need 8 inverters. I certainly don't want to draw 8 inverters, so there's a shortcut everyone needs to know about. This is A coming in, this is going to be A bar. These are both 8. This is an inverter with 8 inputs, no such thing, but this is actually shorthand notation for 8 inverters. Everyone knows that and understands that, and so be sure to use that in your documentation when you can. Next thing I want to do here is add 1 to this thing. I'm going to add 1 via the other input. That's also 8 bits. So what this is doing is complementing the A input, adding 1 to it, and outputting a value. And this is 8. So once again, what I've done is I've implemented this equation, complemented the input, I've added 1 to it by hard coding a value of 1 on the B input. The output is going to be the same as the input but multiplied by -1. The important thing here is this in matches this in, this out matches this out. If those didn't match, it would be questionable, like what exactly was going on. So realize that this circuitry right here lives inside of this box. Now the other way to do the circuit is to use the carry in, out. We've seen that. So what I'm going to do here is in. I'm going to complement that thing. This is the bus here. Before the previous diagram, we used the B input to add 1. This time, what I'm going to do is ground the B input. By grounding it, makes it 0, and I'm going to indicate that I'm setting the carry in to a 1. So the way this circuit is drawn is RC, inside the RCA is going to be A plus B plus carry in. This B is connected to 0, so essentially going to be this A input plus the carry in, which we've hard coded to 1. And so that's the second way to get this equation implemented. Two different forms, both equally as valid. I'm going to check over this. I got the buses marked. I got the names matching. I've labeled the interior modules. I'm going to call this done. This is actually an extremely important problem. It's a circuit that adds 2 to an input value. So, and also it has a valid output. Now, let's go ahead and draw the top level black box diagram for this. And I'm going to, let's call it something. We'll call it RES for result. It has a valid output. I didn't want to call it val for value because it looks like value. It looks like valid. This is a special circuit in that I'm going to say, I'll just say it gets an A, and what it's going to do is add 2 to A and then determine whether the output is valid or not. Now the issue is when we add 2 to some number, there's a chance that it's going to overflow, and we need to check for that. So this is going to be the first circuit we're going to design an extra circuit to check for the overflow. So there's top level marked. I understand the problem, since it's a problem where I have to do an addition and check to see if the result is valid. Only way I know how to do addition is with a ripple carry adder. And what I'm going to do here is take that A input and add it. What else am I going to do here is that ripple carry adder. We'll go ahead and label these. It has another input which is going to be 2. I'm hard coding that input to 2. It's 8 bits and looks good. The issue is that the result may not be valid. I need to design simply a valid detection circuit for this. And so the way I check for valid on RC numbers is to check the sign of the 2 input operands and check the sign of the result also. So if I add 2 numbers of the same sign and I get a number of a different sign, that's invalid. Those are the 2 things I'm looking for on this problem. Now I'll go ahead and do this, and what I'm going to do here is I know I need to check 3 bits. What these are the sign bits. These are all sign bits. So it's a sign bit of A, it's a sign bit of this hard-coded value, which is always 0. We're going to pretend it's not, and the sign bit of the result. So we have 3 inputs, and what we have on this thing is a valid output. This is my valid output. Looking good. There's my validity checkbox. I have a name for it. What I need to do is brute force design this thing with S, A, and B. So we'll go do this A. This is my valid. So what I want to know is essentially when the output is valid. So what I'm going to do is look for, I know it's valid 6 times, and there's 2 rows where it's not valid. So if these are the 2 rows here, if the sign of the 2 inputs is 0 and the sign of the output is 1, that's not valid. The sign of the 2 inputs are both negative and it results in a positive memory output, that's not valid either. So these are the two rows I'm interested in. And so these are going to be, these are not valid, these are valid. And so I'm going to write an equation for, I'm going to do a POS equation for this, simply because it's I only have to do these two rows. So this is going to be complement each side, bring this to POS form, so this is going to be A. So this is my equation. It defines what's in this box, and then I am officially done with this problem. Once again, to go over this, there's a chance that this problem may overflow the range, and I need to indicate that with the valid. I've decided to brute force this design, and which means start with a table. And here's the result of my table. I could have put all the ones down there, which would have given me 6 terms. It's not worth my time. This is a better approach. I actually used a POS rather than SOP approach. That defined what's in this box, therefore this circuit is completed. This is our last example, and it's a real classic example in digital design. Essentially what I'm doing is using one piece of hardware, which is going to be a ripple carry adder, and I'm using that to either subtract or add two numbers depending upon some type of external signal. In this case, there's going to be a signal here, sub, that it's going to decide when that's asserted, it's going to subtract. It's not asserted, the circuit's going to add. So the circuit, let's do this first. Add a little extra line there. I think they're 8-bit inputs. We'll label that, and it has an 8-bit output. The one thing here is, unlike the previous problem, this problem states that the answer is always going to be valid. Just simplifies the problem. What's going to happen in this problem? I'm going to do one of two operations. It's going to be B, and this is when sub equals 1. I mean, this would be an easier problem to do in a later chapter, but there's a point to this. Okay, so what's going to happen here is I'm always adding A, but what happens with B is sometimes I'm adding B, sometimes I'm subtracting B. So when I'm subtracting B, it's going to essentially, what I'm going to do is add a B bar plus 1. When I'm adding B, I'm just going to add B. Okay, so the issue here is when the S input's a 1, I need to toggle all the B inputs and then add 1. Otherwise, I don't need to do anything to B. So this is a real classic circuit in digital design. Obviously, I need ripple carry adder. We decided that A was connected directly. You don't have to worry about this. But B is going to do something different. I'll just give this box a name. This is the B input. B here, it's an 8-bit signal. And what's going to happen is the sub is, depending whether the sub is set or not, it's going to decide whether it sends B over to here or B bar. Now, additionally, when sub's a 1, I want to send it to the carry-in. That's going to accomplish this one. If the sub was a 1 on this circuit, it's going to give me a toggle of all the bits. So what we have here is essentially this magic box sign here, and what I need to do is define that. What I'm going to do is take advantage of the fact that using exclusive OR gate, tie one of the inputs to a 1, it becomes an inverter. Now we're not going to tie anything to a 1, but what we're going to do is use an exclusive OR gate and tie it to the sub. Now what happens when you do that is this circuit, and this is going to be 8. It looks like a exclusive OR gate with 8 inputs. It's no such thing because exclusive OR gates only have 2 inputs. This is shorthand notation to say I have 8 2-input exclusive OR gates. Each one of them is connected to sub, and for one input, the other input is one of the inputs of B. It's going to look, I'll draw the like this. I'll do this real fast. These are the outputs, the 8-bit output, but the sub is common to all these exclusive OR gates. The other inputs of those exclusive OR gates are the individual bits of B. What this says is there's 8 exclusive OR gates that look something like this, but I don't want to draw them. Okay, and lastly, let's finish this up. 8, named it val. We don't have a valid output, so this value, everything seems to be marked well. I'll just call this B prime, just to make it clear. And I'm going to call it done.